Alright, in this video I'm going to start on solutions to the time-independent Schrodinger equation in an infinite rectangular well. And so I've drawn kind of the diagram that you will often see for this right here, where we have this well where on both sides, so here and here, we have an infinite potential, but then inside we have zero potential. So we go right from infinity to zero instantaneously here at both sides. And the width of this well is x here, and this is how it's usually done. You could do it also maybe with x equals minus a over 2 and then x equals a over 2, but this is kind of a standard way where we start with the origin right here where with x equals 0 and we have it go to x equals a. So the length, well, I guess the width of our well is a. So a can be whatever whatever you want the well size to be. And we'll see later that the well size does have, well, when we get past the infinite rectangular well, the well size does have some impact on the solutions to the Schrodinger equation, but we'll get to that when we get to it. So a way we can think about if you want a little bit more of an intuition about this infinite well, this infinite rectangular potential, then we can maybe think of it sort of like if we have this box or something where both sides are perfectly elastic walls, so something can bounce off of it without losing any energy, and we have a frictionless surface, and we can have this mass here, and it'll, if we set it bouncing, it'll keep bouncing for eternity. And when we say that it's infinite, we're essentially saying that no matter how much we start moving this mass, it's never going to get up and out of this box here. And so that's kind of what this frictionless this infinite frictionless well here is doing. And we can say that this infinite potential here is sort of like a force that's pushing this way, and this one is a force that's pushing this way. And so there is, and it's infinite, so if we have something in here, there's no way that it can actually get out of here. You would need to input infinite energy for something to get out of here, and infinite energy doesn't exist. So we say that it's inescapable. All right, and so as I said, this is the time-independent Schrodinger equation here, and I showed in the previous video that we can write this then, if we can rearrange some things here, and we have the second derivative of the wave function psi with respect to x is equal to minus 2m over h bar squared, and we have e minus v acting on our wave function here. And then we sort of defined all this as k. So we said k was equal to 2m over h bar squared, e minus the energy minus the potential, and this was the square root, so that we could say that if we have the second derivative of the wave function with respect to x, that this is equal to, so we have that minus sign there, minus k squared, and then the wave function there. So we can say that inside the well, since v is 0 inside the well, then we can actually say that k is equal to 2m over h bar squared e, and then v is just 0. So we can have this, and this tells us that k is proportional to the square root of energy here. All right, and so we first want to figure out sort of what the wave function will be at the sides, and well, I'll just tell you right now, it has to be 0 at the sides. There can't be any wave function that goes outside of here because, like I said, it's infinite potential, so you need infinite energy to get outside of it. And so our wave function needs to be 0 at x equals 0 and 0 at x equals a. So if we want to look at x equals 0 first, then we have our wave function here, which is a function of space, and we're at x equals 0. And so that is going to equal a e to the I k, and then we're putting 0 in for x, so I'll just put that in parentheses like that, and then plus b e minus I k, k, and then x is 0, so we'll put 0 in for that. And we want the wave function to equal 0, so we set this all equal to 0. Well, anything to the 0th power is 1, so this just simplifies to a plus b equals 0. And so we know that then a has to equal minus b, and that will help us here as we try to figure out then at the x equals a on our infinite rectangular potential there. So if we want to figure out at x equals a, then this will be a e to the I k a. And then, so we're substituting in a equals minus b for up here, so b equals minus a. So we'll make this plus into a minus a e to the minus I k a. And once again, we want to set that equal to 0 because we need our wave function to be 0 right there. And so we can just factor out these a's, and then we have a e to the I k a minus e to the minus I k a. And this will equal 0. Well, there are two ways we can have this be equal to 0. If a equals 0, or if everything inside the parentheses here is equal to 0. We don't want a to equal 0 because that's our amplitude, and if a is 0, then we have 0 amplitude, and that means there is no particle. There's nothing inside the box. And so we need all of this to equal 0 here. So we will then say that we need it so that I e to the I k a minus e to the minus I k a, that must equal 0. All right, and so from here we then want to take so we have this right here, and if we take our inverse Euler for sine, so the inverse Euler identity for sine, so that is sine of x is equal to e to the I x minus e to the minus I x over 2I. So I'm not going to prove this. This is just kind of an ID. Sine can be written as this. I mean, if you want to plug in numbers for x, then you will find that you'll just get the same thing as if you do sine of x. And so we will use this identity here. And as we can see up here, that is essentially what we have right here. And so we can say that this, so we just do some rearranging. You essentially just multiply both sides by 2I. We then have that our e to the I k a minus e to the minus I Ka is equal to 2I sine of Ka. Well, I should also, because we need to have this A here, we'll put that A right there. And so then what we can do is just sort of absorb that 2I into A, and we'll call that A prime. And so we then have e to the I Ka minus e to the minus I Ka equals A prime sine of Ka. All right, and so we need this to still equal 0. We need this to equal 0 because when we're at A, remember this A is where we are in the x here. So x is equal to A. A is the length or the width of our well here. So if we want this to equal 0, we've already said that A doesn't equal 0. We've ruled that out because if A equals 0, then there's just nothing in the well. So we know that sine of 0, if we have sine of 0, that equals 0. So we could say that Ka is equal to 0, but once again, that would just mean that there's nothing in our well there. So there's just so we need Ka to equal something else other than 0. Well, if you know your trig functions, then you know that sine of any integer multiple of pi is also equal to 0. And so we can say that Ka has to be some integer multiple of pi. And so then we can actually just kind of divide both sides by A, and then we'll use K, and we'll sort of suggestively put an N here, telling us that there can be multiple versions of K, and that equals N pi over A. And so with this, we know that integer multiples of pi divided by the width of our potential well tells us what the k's are. Remember that k is related to the wavelength. It's inversely proportional to the wavelength of our wave, and so that is so we always just kind of have to remember what k sort of physically is telling us. And so you can see here that different k's are going to mean different wavelengths, and larger k's are going to mean smaller wavelengths. And so we'll see in future videos. We have our well here. And you may have seen this before where if n equals 1, then we have something like that. If n equals 2, then we have something like that where the wavelength is now half what it was when n equaled 1, and we'll get into that more in future videos, but we'll continue moving on here. So we said before, remember, that we have k is equal to 2m over h bar squared e. So if you remember, we had that. So k squared is equal to 2m h bar squared e, which we said k was equal to this. And so k squared is going to be n squared pi squared over a squared. And so then if we do some rearranging with this, if we want to get this set equal to e, then we will just multiply both sides by h bar squared and divide both sides by 2m. So we end up with E, and we'll put an N there because we can have different energy levels. Each of these is a different energy level. And we have E is equal to N squared pi squared H bar squared, because we multiply both sides by H bar, and then that is over 2m, because we divide both sides by the 2m, and we still have that a squared there. So this is what the energy equals. In these, this E here is an energy, is an eigenvalue. So an eigenvalue. So if you remember our Schrodinger equation, you'll often see in this form here equals E multiplied by the wave function here, and the H, if you remember, that was from before, from our time-independent Schrodinger equation, H, or minus H bar squared over 2m, the second derivative. Actually, I'm going to leave that out of there for this, since I'm just looking at the actual Hamiltonian operator here, plus v. And so this was our Hamiltonian operator, which is what we have here in our time-independent Schrodinger equation. And so this is an operator. And if you remember from my videos on spin, where I talked about how we have a Hermitian operator, and I was using the Dirac formalism in those videos, and that is equal to some eigenfunction here multiplied by the ket vector. And so it's the same form as that, where we have this operator. It's just that instead of the operator being some square matrix, so instead of being something that looks like this when we were doing spin, this is the Hermitian operator right here. And that is why E here is an eigenvalue. So the Hamiltonian here is the energy operator. There are other operators we can act on wave functions for quantum systems, and we will see those in the future as well. We have things like the momentum and the position operators, and we'll get into that more in future videos. But right now we're talking about this Hamiltonian operator, which is the energy operator for the wave function. All right, and so as I said, that is an eigenvalue, and so it's the eigenvalue. If we use the Hamiltonian operator on the wave function, then it will give us these eigenvalues, and it depends which wave function it is, will tell us what the actual energy is. So, like I said, if you remember from my videos on spin, we had the Hermitian operator, and if we acted it on this ket vector here, that would give us some eigenvalue here multiplied by the ket vector. But if we took that same operator and operated on some other ket vector, then it would give us a different eigenfunction multiplied by that ket vector. And so if we say that, well, if we have different if we have these different eigenfunctions, these different wave functions, which I kind of alluded to right here, where we have maybe a single, well, a half wave inside the potential, or we have this full wave, or you could even then have solutions that have something more like this, and so on and so forth. As long as they're zero at both sides, then you can have pretty much, I mean, in an infinite well, you can have any number of waves inside of the well. We'll see later that if it's not infinite, then there are, then you can't have essentially an infinite number of waves inside there. But we see that there are these different wave functions, and if we have the wave function that is just the half right here, and we act on that with the Hamiltonian operator, that will give us a particular E, a particular energy, which is determined by this right here. But then if we acted on a wave function like that, then that would give us a different E. So this one would give us one where this N here equals 1. This one would give us one where this N here equals 2. And so this energy here is sort of, well, I don't want to go too far with it, but you could almost say it's kind of a function of this N here. And we obviously see that the width of the well and the mass of the particle and stuff are all important for this as well. But yeah, anyway, that is sort of, I hope, an intuition of what the Schrodinger equation is actually doing. And so it's essentially solving for these energy eigenvalues. We will see later, though, that it's not as simple really as we have, this wave function, and that is definitely this. So we could call that 1. We have this, and that's definitely this. But these can actually be linear combinations. So the actual wave function could be a linear combination of a bunch of these, and so yeah, and that could go on to to a lot of them. I guess infinite of them, really. But anyway, we will get into that more in later videos. But I just wanted to give a little bit of intuition here as to what this E actually is. That is the energy of the system when we are using the Hamiltonian operator. And Hamiltonians, if you have ever taken classical mechanics, there are Hamiltonians there as well. And Hamiltonians are always the energy of the system. So if we have some Hamiltonian, then it is, in classical mechanics, you'll see it written kind of like this, where it equals the kinetic energy plus the potential energy, and that is sort of the form that the Schrodinger equation is taking, where this part here is the kinetic energy and this is the potential energy. And so anyway, I think I've probably rambled on long enough about that. We will continue sort of looking at this idea of the infinite well here in the next maybe even up to 3 videos. Definitely going to take 2 more, I think, but maybe even 3. So stay tuned for those, and hopefully after these few videos you will have a little bit better intuition about about what the solutions to the Schrodinger equation actually mean. And then we will show, because the infinite rectangular potential well is this sort of idealized system that doesn't actually exist, then in future videos after these ones, I will talk about the finite rectangular well, and then the actual sort of, I guess, parabolic or harmonic oscillator well, and then also the free particle. And then I will actually start going into some of what the Schrodinger equation tells us about things like atomic orbitals. And so, uh, yeah, I'm a chemist, so I feel like I have to cover that stuff. I am trying to make this more of a just quantum mechanics playlist, not too much, not trying to make it too chemistry based, but as a chemist, I have to do that. So, anyway, I will stop rambling now. I will see you in another video.